with the talk by Mirko Kurti, What Drives the Scatter in the BBT Diagrams, a Machine Learning Base.
Can you hear me?
Yes.
Okay, can you see my full slide?
Well, we see it in presenter mode.
It's okay, no, sorry. So, just... Okay, can you see it now?
No, we see your screen. We don't see the presentation. Now we see it. Okay.
Okay, great. Okay, thank you. Sorry for that. Hello everyone. My name is Mirko Kurti. I'm a postdoc at the Kavli Institute for Cosmology at the University of Cambridge. And first of all, I would like to thank very much the organizers for organizing this beautiful conference and giving me, not really admit a machine learning expert person, the possibility to present this work, which has been recently submitted to RAS and should be available on the archive early next week. So if you want to know what we have been doing much more in detail, just keep an eye for it in case you're interested. Just a brief introduction of what and why the BBT diagrams, what the BBT diagrams are and why they are important in galaxy evolution studies. Well, diagnostic diagrams in particular, and in particular BBT diagrams, so diagnostic diagrams based on rest frame optical emission lines, have been used extensively in the literature in the last 20 years to infer properties of the ISM in galaxies, and in particular to discriminate between different ionization sources in galaxies, and for instance, to discriminate between ionization coming from a recent star formation within H2 regions, or if the dominant contribution to ionization, for instance, comes from AGN activity or different kinds of stellar populations. And the distribution and the relative location of galaxies within these diagrams, of course, contains a lot of physical information, which is, can be extracted, for instance, by modeling the position of galaxies within these diagrams with different prescription and photoionization models, which in general are pretty much good in reproducing the average position of galaxies within these diagrams by tweaking different input parameters, but they're often affected by a lot of degeneracies, so that it is quite difficult to really disentangle which is the relative contribution of each physical quantity to the position of galaxies within the diagram. Moreover, it has been clearly seen in the last decade that galaxies at high redshift behave quite differently when plotted onto these diagrams with respect to their local counterparts. And they show, for instance, a clear offset from the median position of the galaxies in the local universe in, for instance, the N2BBT, which is the BBT diagram based on the oxygen 3 over H beta and nitrogen 2 over H alpha emission line ratios. So the idea behind this work was to try to build a framework which is purely based on observational data and is free of any underlying assumptions about correlation, linearity, monotonicity within the data. So try to implement, as I will show, machine learning methodologies to describe the position and the scatter in particular of galaxies within these diagrams. So we started just by looking at the distribution of star-forming galaxies from the Sloan, from the SDSS, in the N2BBT diagram, which I'm showing here. And in each panel, I'm showing the distribution of star-forming galaxies is color-coded by different physical properties, like stellar mass, star formation rate, gas phase metallicity, ionization parameter, electron density, and so on. And then, as we can see, we can immediately see some interesting things here. In particular, that star-forming galaxies form quite a clear sequence in some of these properties along the N2BBT, for instance, in stellar mass, in gas phase metallicity, in ionization parameter, here traced by the ratio between the oxygen 3 5007 and the oxygen 2 727 emission lines, or in the N over O abundance. And that in particular, if we look at the white lines, white contours, which trace the isocontours, so the lines of constant value in each parameter within the diagram, we can see, for instance, that isocontours in metallicity are quite orthogonal to the median location, to the median sequence of galaxies in the diagram, as parameterized by this red curve here, almost anywhere, everywhere along the sequence. So the idea here is that, okay, it seems that, and we can also try to quantify it with different statistics, which are described much more in detail within the paper. Okay, we can assume to the first order that the sequence of star-forming galaxies in the N2BPT, in the local BPT diagrams, are primarily a sequence in metallicity. So that moving along the sequence, the median sequence of star-forming galaxies, change the value in the metallicity, whereas lines of constant metallicity are almost everywhere orthogonal to the sequence itself. So following this basic assumption, we try to build a framework in which we describe instead the scatter, and in particular, I would say the deviation of galaxies with respect to the median locus in the BPT by means of relative variations in a variety, in a set of different parameters. For instance, stellar mass, star formation rate, nitrogen over oxygen abundance, ionization parameter, gas density, stellar age as probed by the D4000 index, velocity dispersion of the gas, and so on. So the idea is that here we are considering each galaxies to be offset from the median sequence following a purely orthogonal offset, so basically computing the Euclidean distance within the diagram. Again, as I said, the offset is associated to relative variations in different physical parameters, and that the offset is at first order occurring at fixed metallicity. And so here I'm just showing the same plot as before, but here galaxies are not color-coded anymore by the absolute values in each of the parameters, but by the relative variation in each of the parameters compared to galaxies lying on the closest point along the sequence, along the median sequence of star-forming galaxies in the diagram. And so these kind of relative variations in each of these parameters provides our set of parameters which we'll use to feed different machine learning algorithms and try to solve basically two standard problems. On the one hand, a rather simple classification problem trying to predict whether a galaxy simply lie above or below the median sequence of star-forming galaxies in the BPTs, and a regression problem where instead we're trying to predict the exact magnitude of the offset from the median sequence itself. And to do so, we have started at the beginning implementing artificial neural networks whose hyperparameters and properties are briefly described here in the slide, with the aim basically of assessing and characterizing the maximum predictive power of our set of parameters. And this is done on the one hand by feeding the network with the data set for each parameter individually, and also by feeding it with a set of multiple and independent parameters in order to characterize and assess the maximum predictivity of the whole set. Here I'm just showing the results from the artificial neural networks run on the N2BPT in particular. And we can see that when the network is fed with a multiple set of parameters, it achieves quite a high accuracy in the classification tasks, higher than 90%, and quite a good result also in the regression task, which is quantified here by these improvement over random statistics, which basically quantifies how much each parameter or set of parameters perform better with respect to a purely random variable, which by definition does not contain any true physical information in it, okay? Whereas in terms of individual parameters, so when the network is fed with one parameter at a time, we see that parameters which trace relative variations in the nitrogen over oxygen abundance are the one which performs best by far with respect to all the other parameters in our set, in describing both in the classification and regression the offset of the galaxies from the median sequence in the N2BPT. We have also implemented random forest in order on the multiple parameter set in order to try to understand and disentangle the relative importance and the relative contribution of each of the parameters in setting the offset from the median sequence. And the results also here are quite clear. parameters associated with deviations in NRO carries almost the full information, or most of the total information. More than 8% of the relative parameters importance is kept by variations in NRO, whereas small but significant, I would say, residual and complementary importance is retained by properties that are associated with the age of galaxies and the specific star formation rate, namely the D4000 and equivalent width of the H alpha. And the interesting thing here is that, perhaps not surprisingly, most of the relative importance, well, the relative importance of most of the parameters in the set are strongly suppressed with respect to their individual predictive power as determined by the artificial neural networks. And this suggests that their individual predictive power just came from intercorrelations with other parameters, whereas the main information is carried by the deviations in NRO. Okay, so the result in terms of the global behavior in the diagram, sorry?
1 more minute.
Okay, thank you. So the information in terms of the global behavior in the diagram is quite clear, but you could say, okay, you're considering the offset orthogonal to the median sequence at each point, but as you move along the sequence, the inclination of the offset vector, I would say, with respect to the x-axis changes as you consider different positions along the sequence. And so it changed the relative amplitude of the two components of the offset, the component along the x-axis and the component along the y-axis. So is this affecting somehow the relative importance of the parameters as we've seen before? So to test this, we've just implemented this simple test. We have divided the BPT diagram, the sequence of star-forming galaxies, into 4 separate sectors and repeated the analysis. And so this is what we get in terms of both individual predictive power and for the full set from the artificial neural networks and the random forest. Here I'm just showing the classification, but regression results are more or less the same. And we can see that deviations in NRO are ranked first in the artificial neural networks everywhere along across the diagram, regardless of the relative inclination and the relative importance of the two components of the offset vector, and even the random forest. And deviations in NRO are the one maintaining the highest importance. I would just like to briefly show that we've done the same for the S2 BPT, of course, with the same approach, finding quite a different result, in which, in this case, for the S2 BPT, deviations in the star formation rates are the one retaining most importance, and the one which the highest predictivity from the artificial neural network, and the one with the highest relative importance in the random forest. And we interpret this in terms of the fact that in high star-forming galaxies, H regions might merge together at a certain point, reducing the effective size of the S+ emitting regions, which affect the emission in the S2 emission line, and so affects, of course, whether a galaxy is offset
can you please,
in this region in particular with respect to the median sequence.
Please conclude,
so this is it. Next, I'm done. So next thing, of course, to test it on high redshift galaxy sample, in particular with JWST and moons, which will allow SDSS-like surveys at redshift higher than 1. And I'll just leave my summary slide here. Thank you very much.
Thanks, Mirko. Applause. So we are running late. Do we have quick questions in the audience here? Do we have questions on Slack?
Yes, there is one question from Aritra Ghosh. Have you checked whether there is a chance in your results if you consider a subpopulation, a subpopulation which is X-ray detected here, whether how much the results vary with obscuration?
Okay, no, so this is a good point, but basically at this level, the analysis is just based on local SDSS star-forming galaxies. And of course, we are also considering extinction of obscuration via the Balmer decrement, but the point is that these diagrams are by definition insensitive to extinction because they involve lines which are very close in wavelength. So any, I would say, importance which might be retained by, for instance, the Balmer decrement should come from intercorrelation with other parameters, because extinction could not directly affect the emission lines of these diagrams in particular. So I don't know if this answers your question, but maybe we can discuss later on the Slack.
Thanks, Mirko. Let's thank Mirko again.
Thank you.